Well, okay then. It is already the 61st episode of Space Rocks Uplink. Going to bring Mark McCorkran in and begin what's going to be an exciting and timely episode. Mark, how you doing? Are you receiving?
I am. I'm good, Alex. Yes.
Very good.
You're looking very green there.
It's a bit weird. I think I might just have to change the light on here. That's it. Am I?
Yeah, it's not St. Patrick's Day. I'm not quite sure what the look you're going for there, but
Oh, that's fantastic. Here, we'll just yeah.
oh yeah, just keep them strobing, changing.
Excellent. Yeah, it's always fun with the lighting setup here. So, Mark, there's no beating around the bush here. It's been an eventful week in the world of space rocks as well as the world of space exploration as well. Now, people who've been following us online will, of course, know we were due to make an appearance at the Science Museum with one of our great friends, Anna Phoebe. And, that's unfortunate that we couldn't, but we kind of felt like we had to make a stand on a very important issue, which is, of course, so pertinent to the things we talk about on Space Rocks all the time. It's about Earth as well as space, and what's down here being just as important as anything else that's out there. In fact, Mark, we talk about this all the time. It's by looking out there that we realize just how fragile our habitat is. And so when the Science Museum began working with fossil fuel companies, we kind of felt like, well, we should probably step aside and let them sort that out. And we're looking forward to working with them again when things change over there. I'm hoping that the kind of messages that we and many other people are sending will be heard by the right people, and we will have to see what happens.
Yeah, and I know this is something Anna felt very strongly about. So, we fully support that she didn't want to perform yesterday. And, again, she's a great friend and somebody we'll work with definitely a lot more in the future, and hopefully with the Science Museum as well.
Indeed, indeed, indeed. And of course, it's not just about space rocks altering its trajectory. It seems that some actual timings for the James Webb Space Telescope, of course, the subject of our last Space Rocks uplink. Exciting times, but a bit of a jitter. Is that a fair description?
Yeah, I think so. So a couple of weeks ago, during the ongoing test phases and installation, if you like, of James Webb Space Telescope on top of the Ariane 5 rocket, which will put it in space, there was a moment where there was an unexpected release of what's called a clamp band, so component which holds the observatory to the launch adapter. And that released unexpectedly and generated a big shockwave which went through the observatory. Now, people would say, well, surely the observatory's built to operate after being shocked, in the sense of when it gets launched, all that noise and vibration. This is a very specific kind of like whacking it on the side with a big metal hammer kind of vibration. And there are some components on JWST which needed to be checked, essentially, and needed to be looked at, see if they were still functional. So the decision was made to take it back into the integration hall, plug some wires in, make sure everything was still working. So what that's ended up doing, and it was announced last night, is that's resulted in the launch date being slipped from the 18th of December to the 22nd of December. So very close to Christmas. It's going to be an interesting rush around the world for those involved, and the scientists, the engineers, the media, and so on. But
Indeed.
fingers crossed, it will be the 22nd of December. And just for everybody to keep in mind, that's 9:20 in the morning in Kourou. So depending on where you're living, you should be able to figure that out. But in the UK, for example, that's around lunchtime. So and a bit later in Europe, and on the east coast of the United States, 7:20 in the morning.
Well, an eventful way to round out the year, certainly. But of course, that's not the only thing that's happening. Before a lot of people break up for the holidays, and of course, what's about to happen is extremely interesting. I mean, and what I love about this, Mark, is on Uplink, this is one of the missions that we've followed multiple times. Just at the different stages from launch and onward. I think it's so good that we kind of, I think we've created chapters around it all. So what is this next chapter? What's about to happen, and who do we have on tonight?
Well, the mission up here behind me is the ESA-NASA mission Solar Orbiter, which is a combined mission to study the sun and the solar wind. So to study the sun from a distance by looking at it, but also study the particles coming past the spacecraft as we're quite close to the sun, and we want to be much closer in than where the Earth is in order to be able to see the sun from closer up, get higher resolution pictures, but also before the solar wind gets disturbed as it moves away from the sun. And in order to change the orbit of solar orbiter, as we'll hear from our guests, we need to use planetary flybys in order to change the orbit from something close to the Earth to something going inside the orbit of Mercury even. And ironically, we're going to do that this coming Saturday morning by flying back past the Earth for the first and last time. Solar Orbiter's been past Venus and used Venus a couple of times, but this Earth flyby is the first and last. And it's an interesting one because, of course, we live here. This is where we are. And not only us, but all of our junk up in space. So as we'll hear from the guests who we have on, a little bit riskier than a Venus flyby. And so the two guests this evening are Anik De Groof. She is an instrument operations scientist on Solar Orbiter. She's a solar physicist, has worked on several missions, and we'd like to talk about some of those as well. And she's based at ESAC near Madrid in Spain. And as I say, she's an instrument operations scientist, so intimately involved in the planning of the kind of observations we'll start doing after this Earth flyby. And our other guest is Louise Harra, another solar physicist from the UK, but is currently the director of an institute in Davos, which many people know, of course, from the big meetings of rich people who get together in Davos once a year to discuss the woes of the World Economic Forum. And but there's an institute there which is devoted to studying the sun. And Louise is the director there, but she's also the co-principal investigator of one of the instruments, the extreme ultraviolet imager on Solar Orbiter. She had a lot of background with other missions as well. So two people that are right at the front line of what this mission's all about scientifically and operationally.
Indeed, and of course, given the proximity of this maneuver, I guess we're especially grateful of them sparing the time, because I imagine some full inboxes. So without further ado, let's bring them aboard. There we go. Let's just always give it a minute. There we are. How are you doing? Are you receiving? There we are. How are you doing? Are you receiving?
Yes.
There we are. How are you doing? Are you receiving?
We have the ultimate feedback loop somewhere.
I'm going to suggest if you're watching this on YouTube over there, if we turn it down, you don't have to hear my horrible voice more than once. There we go. Anik, how are you doing? Are you receiving?
Yes, I'm receiving.
Fantastic.
Good evening.
Well, good evening, and thank you both so much for joining us. We know it's going to be a busy few days, and it's such a pleasure to have you here. And so look, I've got to start with a kind of a broad one. It's how we usually kick these interviews off, simply because, well, I've got to ask an obvious question that might be going through the minds of people. We look at the sun every day. Don't we know everything we need to know? Anik, what do you think about that?
Well, actually, indeed, the sun is the nearest star to us, and we see it every day. So you could say, well, we must know quite a lot. And indeed, we do know quite a bit about the sun. We have been studying it for many, many years, first only from Earth, and then also we started exploring it from space as well. But still, our knowledge is quite limited. And the main thing, so we learned a lot about the activity on the sun and also how it can affect Earth. But one of the things we don't really know very well yet is how does that effect of the activity come towards us? I mean, what happens between when it starts on the sun and when it actually reaches Earth? Because we have been mainly studying the sun from the viewpoint of Earth and also from the distance of Earth. And this is one of the things that definitely we are lacking in our understanding.
So Louise, you, as I said in the introduction, you run an institute in Switzerland which has devoted itself for many years to studying the sun. Initially, I guess, I don't know the full history actually, maybe you should take us through it of what your institute has done. You know, before the space age, it's been around for much longer than that, as I understand. So this idea, again, as Anik said, we've been studying it for a long time from the ground. What have we been able to learn from ground-based observations, so to speak?
So the institute in Davos was formed over 100 years ago, and the purpose of it then was to understand the atmosphere at high altitude. So why is the atmosphere here better for patients with tuberculosis? So it started from that basis of trying to understand the environment here, why it was good for people. And then, of course, as time progressed, these observations developed, the accuracy of them developed. You're studying the irradiance from the sun, you're studying different wavelengths, aerosol optical depth, ozone, those kind of things. They've been studied for a long time. And now, of course, the big push behind the work is climate change. So making sure you've got as accurate measurements as possible that feed into climate models for prediction and for solar energy companies. So it's moved from tuberculosis to understanding climate change.
So let me dig in on that just a little bit before we move on to the space missions. So it's always remarkable to me, you know, how large the errors have been on our ability to measure the brightness of the sun. And it's not, of course, just the visible light, but the entire intensity across the whole electromagnetic spectrum. Why is that difficult? What's the problem with just, you know, going out there with a very sophisticated thermometer and saying it's giving this much light out?
I mean, actually, in our institute, we hold the world standards for irradiance, and we just had in September a calibration campaign where countries around the world brought their instruments to us to calibrate to our world standard. So you need the accurate measurements so that everywhere globally is measuring to the same standard. And that is only done by bringing those instruments together. So instruments degrade, you know, they change with time, they can change in their environments. So you need to be able to make sure the calibration is done well.
So just again, I think probably people don't often understand that many of the things we do in astronomy and space science are often relative measurements. We're very good at doing accurate measurements of A versus B in space. You know, this star is 10 times brighter than that star. But absolute measurements, you know, saying this number of watts per second, per whatever, is actually very tricky. So, and of course, the basis in climate change is you've got a few people saying, oh, it's just the sun changing its brightness. And if it's giving out more heat, of course, we're getting warmer. Nothing we can do about it. Let's just keep burning oil to make ourselves comfortable. But that's just not the case, is it? I mean, we know definitively that's not what's going on.
It's absolutely not. I mean, I think the evidence is so clear that it's human-made impact on the climate that's causing the change. It's this the fluctuations that we see in the sun. Obviously, the sun provides the radiance, the heat and light for us here. So it's a big component in the climate models, but it's not what is causing those temperature increases that we're seeing. At the recent COP26 meeting we're discussing, it's just not what's causing that. It's clear.
And so just my last question before I jump back to Alex. Anik, from your perspective, I mean, of course, the sun does change. It is not a static object. It's not constant. It changes every 11 and 22 years. It has changed over history. And the missions which we're launching and we fly in space are in part about addressing the dynamic sun as well, how it does change. Even though the total irradiance, the amount of flux reaching us, isn't the changes in that are not enough to explain climate change, but it is changing. It changes from minute to minute, second to second, day to day. So talk us through a little bit about what makes the sun do that. Why is it such a dynamic thing?
Yeah. So maybe first how we got to know that. So indeed, when we started observing the sun from Earth, at first there weren't telescopes yet, so you didn't really see a lot of detail. From the invention of the telescope, people started seeing dark spots, for example, on the sun, what we call sunspots now. And so these seemed to change. Sometimes they were many, sometimes they were less. So people started making daily drawings of the number of sunspots and also where they appeared on the sun. So then they found out there is some kind of cycle in this. And so only after many, many years, they found out there is a cycle of 11 years in which the sun is getting has more sunspots or less sunspots. And so this was very clear from Earth already. Now, what we really learned with going into space, well, the first thing to say is your observations from Earth are limited because of the wavelengths you can measure at Earth, because our atmosphere is protecting us against high energy radiation like UV light and X-rays. But the sun is actually emitting a lot of its radiation in these wavelengths. So only when you send a mission to space and you look from outside of the Earth's atmosphere, you can suddenly see the brighter and the more active areas in the sun. And so it turned out there are active regions very close to those sunspots, and those active regions indeed come and go with this cycle. So what we learned from space is that the sun has a very, very dynamic atmosphere in which the magnetic field and the complexity of the magnetic field gives rise to active regions being formed. These active regions then lose energy in terms of radiation, what we call solar flares. So these are sudden releases of radiation that are being sent out in space, and also sometimes in the form of what we sometimes call solar storms, or CMEs is a better word, where the sun is losing a lot of its material in one go, and you get kind of a cloud of magnetized and highly energetic material being thrown away into space. So this is actually really what we have been learning from space, and that's why it's so important to have space missions looking at the sun.
So, it's interesting, of course, because I mean, we're talking about, just like massive fluctuations in energy and what's being thrown off of the sun. But it sounds like one of the riskiest things that's happening is not actually this remarkable instrument's journey to the sun, but what's about to happen as it comes back around the Earth. Now, I've seen this described as a risky mission here and there. Anik, why is that? What's going on? And why is coming back to Earth such a tricky proposition?
Yeah. So first, the mission now comes back to Earth because we want to use the gravitational pull of the planet, of Earth, to change the orbit of the spacecraft. And we do this several times in the mission. Because in the end, we want the spacecraft to move closer to the sun. And to do that, you have to kind of decelerate the velocity it got from being launched from Earth. So you need to kind of fall towards the sun. So that's why we do these, what we call gravity assist maneuvers. Now this one is close to Earth. And the risky thing about it, well, a flyby is always a bit risky because you have to burn the thrusters at the right time. You have to make sure you get to the right orbit, because if you miss the chance, then you can't just go back and try it again. So that's one thing that makes it risky. Now, an EarthGAM is particularly risky because, well, us humans have left a lot of debris around the Earth. And Solar Orbiter happens to pass very close to Earth at an altitude of about 460 kilometers, which is very close, well, within the low Earth orbit where there's a lot of debris. So we have to fly to that zone. And we also have to fly through the zone higher up, the 36,000 kilometer ring, which is the ring where the geostationary orbits are. So these two places are actually two rings around the Earth where many satellites are being operated, and also many dysfunctional satellites are still flying around. And we also have a lot of small pieces flying around. You probably heard about the satellite that got destroyed a bit more than a week ago. So this is another cloud of debris that has been produced, and that is a risk for our spacecraft.
And just for people who are, I think, half of our audience knows this stuff very well, but some, we get a lot of people in from other domains. These are just tiny little pieces, some of it. I mean, of course, if you hit a big satellite, it's kind of obvious that it might cause some damage, but even tiny pieces can cause damage. And that's, of course, because we're moving so fast. So maybe we're talking a little bit about that, right? I mean, we can't predict where many of these things are either. I mean, some of the big things we can kind of avoid, right? We have the opportunity to change the trajectory of Solar Orbiter. When's the last opportunity for that happening? Because the flyby itself is on Saturday morning,
yes.
4:30 in the morning, GMT. But when's the last moment, or is it past already? Could we have adjusted?
No. So the last maneuver that can be done is 6 hours before the actual flyby. So typically what happens is, okay, you're flying a particular orbit, and Flight Dynamics has a very good model and checks very often whether the orbit is still as expected. And so they plan for several opportunities close to a flyby where they could potentially change the orbit a little bit. And so this starts 2 weeks before a flyby, then you have another opportunity 1 week, then several hours before. So 6 hours before is the last chance. And so now, as we speak, they have just measured again the orbital characteristics. They are currently analyzing it. And tonight, I think around 11 o'clock local time here in Spain, we will know whether this last maneuver will be performed, yes or no.
Okay.
And so there are two things here. On one hand, indeed, they can just see, okay, are we on track to do the flyby exactly as we want to do it? And on the other hand, it's also the Space Debris Office that is looking into their models of the debris, because we do have alternative orbits in case we have to do a maneuver to avoid a collision. But up to now, well, all the last news was very good. So we got actually, we got the news that probably no maneuver will be needed for the debris because it's looking quite good. It's true, as you say, only the largest particles or pieces they can really track. So they can really, they know where they are. But there's a lot of very small pieces as well that they have to more track statistically. So it's just a chance you hit a cloud of these little things. Yeah. But so it's looking good. So we keep fingers crossed.
Now, just to talk us through a little bit about, you know, what the actual maneuver with the flyby entails. This is a clip from a movie which is made for that, and so we pass over essentially over the Sahara Desert, right? That's close to the closest approach, and then over the North Atlantic. But will it be visible? I think that's the question people always want to ask. Who will be able to see it during this event? I'm not sure I know the answer to this. I've been thinking about it myself, but you can tell me the definitive answer.
Yes, I don't know all the details, but I know that the best chance to see it is around Tenerife, or even better on a boat close to Tenerife. But the problem is that the magnitude, so you could see it with binoculars, but the magnitude changes very rapidly. And so also the spacecraft itself is moving very rapidly. So you only have a very small chance, very short period actually, where you have a chance to see it.
Because I guess it's coming in, you know, pretty fast, and it will be moving across the sky quicker than the ISS, I should think. I mean,
yes.
Yeah, it's much quicker than being in orbit around the Earth at that point.
Yeah.
I looked at this movie and I played it through, and I thought, oh, it's, you know, the Canary Islands, that would be great as long as you're not living on top of a volcano in La Palma. Yeah. But I'm not sure whether it's illuminated by the sun at that point. Of course, that's the problem. If the satellite doesn't see the sun, then you don't see it either. But,
yeah. So the satellite, this is very important. The satellite always has to be pointed to the sun. So also during this maneuver, we have to keep the solar panels towards the sun, but even more importantly, the spacecraft is protected by a heat shield. And that heat shield, of course, protects all the instruments, all the sensitive instruments, and that always has to face towards the sun. So even in this maneuver, we will not actually turn around the spacecraft too much. Of course, we are very far from the sun now, so we don't have that much radiation, but still, the mission is really designed to always be facing the sun or very close to them.
Mm. Now, the other thing which happens after this is we move into the main science phase of the mission. This is the last gravity assist maneuver before that starts. Not the last gravity assist maneuver. There'll be a whole bunch more at Venus in the future. But Louise, you're the co-PI of one of the instruments on board. It's not as if you've been waiting. You've been doing things along the way since the launch in February last year. So the mission's been going on and your instrument's working. Talk us a bit through what people have been able to do in this sort of pre-main science phase.
That's right. So after we launched, we got our first light, or opened the doors in May 2020, and got our first image then. So the plan for the remote sensing instruments in this period to get into the final orbit, which is called a cruise phase, which sounds like you're cruising along a highway in the US, whatever, is that we do a lot of testing, a lot of checking, calibration work during that time. So we had particular snapshots of time where we could switch on to test how each individual instrument worked, and also coordinating some observations together. So although the plan was not to do science during that time, the data quality was good enough, or better actually, than we hoped, that we've been able to do science and get new results out. But once we get into the nominal science phase, then that's where we truly coordinate between the instruments. And that's what will be really exciting, to be able to finally do that, and to be able to be observing for longer periods of time together with all the instruments together.
So one of the nice little discoveries, that sounds wrong, but little in scale relative to the sun, are these so-called campfires, which were, or nanoflares, which were found with your instrument EUI, and that you needed to be quite close to the sun to see that. So it's not like we haven't been close to the sun yet. If I'm right, sort of half the distance between the Earth and the sun, half.
That's right. So we were at half the distance between the sun and Earth when we took those observations, and that observation was testing high cadence mode of one of the telescopes. So, and it was only a 5-minute duration. But even within those 5 minutes, the data quality was good enough that we were seeing features we couldn't see with other instruments. And the smaller the scale you go, you see more. So when we get into our closest point, that'll be another factor of 2 better. So we know we'll see more of these little features. A lot of work has been done just on that data set already, sort of looking at, because of the orientation of the spacecraft, you can start to do 3D work. So you can start to measure the heights of these things. You can measure the energies of them. How much energy are they inputting into the atmosphere? We know the sun's atmosphere is hot. So as you go away from the sun, it goes from being 6,000 degrees to over 1 million degrees. And that increase in temperature is counterintuitive, and understanding how it's heated, where that comes from, will all feed into that. And also how the solar wind is formed, which you mentioned as well earlier. That this mission a lot of it is about understanding that solar wind.
So we have people watching from all over the place, and I just wanted to bring one of the I think more timely questions in, because it's actually not about the sun at all. Matt Taylor is watching, and he had a question about, so what instruments will be operating during the actual flyby, and what science can be expected right now? Louise?
We'll be off.
Completely off. Yep.
But the in situ instruments will still be on. But for the remote sensing telescope, sensitive filters and all sorts of sensitive optics, we'll be.
So meaning you'll have the doors closed, because the instruments on solar orbiter, you have this big sun heat shield, and then you open your instruments. You don't keep them permanently looking at the sun. And that's a space to breathe in, I guess. You want to close the doors just in case.
It's also during any risky operation like a flyby for us. It's best to be hiding. Safe. Yeah, exactly.
So Anik, talk us through which instruments will be on then.
So the in situ instruments definitely will be on, because also it will be very interesting to combine the solar orbiter data with other spacecraft that are actually measuring the Earth's magnetosphere, because now solar orbiter will suddenly dive into this Earth's magnetosphere. So you have the mission cluster, which has 4 different satellites, and they are studying the Earth magnetosphere, and also Swarm, which are 3 different satellites. And so during the flyby, solar orbiter will also add data from magnetometer, for example, of solar orbiter, and the waves and the high energetic particles instruments. So the in situ instruments will be on. Then Solar HI is also one of the telescopes that is normally not looking straight at the sun, but it's looking further away, like to the high corona, seeing what's flying off the sun, so to say. And so there's a similar instrument also working on Parker Solar Probe and on stereo. And they will also try to measure part of the Earth flyby. But again, as Louise said, there is a period, especially because we will go into eclipse as well. The thermal environment will change a lot in a short time. There is a period where all the remote sensing instruments have to be off because of safety. In the end, we take the opportunities we can during those flybys, but still it's a risky operation. So we have to make sure the instruments are all safe.
So let's pick up on that, because it goes back to Alex's question at the beginning a bit. Why do we have to keep studying the sun? And it's not as if Solar Orbiter is the only satellite that we have studying the sun. So you talked about magnetospheric missions in the Earth's magnetosphere, the magnetic bubble around the Earth, which is affected very dynamically by the sun. But you mentioned a couple of other missions there, Stereo and Parker Solar Probe, and they're in very different places in the solar system. So talk about those and how Solar Orbiter works with those well, 3 satellites, but 2 missions.
Yes, that's actually very interesting now in these years that we have many complementary solar missions flying at the same time. Because as I said before, the first space missions looking at the sun always looked at it from the Earth perspective. Same distance from the sun as the Earth, and also the same viewpoint. That changed when Stereo got launched in 2006. So Stereo is a NASA mission with twin spacecrafts that have orbits very similar to the Earth orbit, but one is going slightly faster and the other one slightly slower. So over time, they actually move one ahead of the Earth and one legs behind. And so after years, then they start separating more and more, and you get a stereo view. Not only a stereo view because of those 2 spacecraft, but you have the Earth view as well with the satellites there. So that was already a very important first step. Now we also have Parker Solar Probe and Solar Orbiter. So Solar Orbiter will have a very unique orbit. It will have a highly elliptical orbit. That's the orbit we will go now into in a few days. So at times it will be closer than Mercury, and at times it will fly again very close to the distance that Earth is. So we want to really explore this whole space in between the area very close to the sun and the place where Earth actually feels the effect. And then Parker Solar Probe will go even closer than Solar Orbiter, but the disadvantage there is that they go so close that they can't take any cameras, any telescopes anymore on board. So Parker Solar Probe will really dive into kind of the extended corona, so the outer layer of the sun, but it will be blind, so to say. So it will measure how the solar wind is and what the effects of the sun are very close to the sun, but it will need Solar Orbiter and also satellites closer to Earth to give the context, what was happening on the sun at that time. And so with all these missions now flying in different positions, we get really very interesting opportunities, because we have configurations where Earth sees the sun at one side, we see it from the side, or we see the far side of the sun. Parker Solar Probe could be aligned with Solar Orbiter and the sun, that we see kind of the same plasma flowing by, first by Parker and then by Solar Orbiter, and then sometimes later by Earth. So you get really very, very interesting opportunities to do very new science.
And of course, we shouldn't forget, Europe has a fleet of these missions, the sun and the interaction with the Earth. NASA does, of course. There's also SDO. Then there's missions, of course, from Japan, and that's something which they've made a big effort on over the years, and that's something you've been very closely involved in, Louise. So talk us a little bit through some of the missions which Japan has been launching. Of course, we collaborate with them on these, Hinode and Yoko earlier, and you were the PI of one of the instruments on Hinode, which is still flying, and talk us through what's complementary there.
Yes, so the Hinode mission was launched in 2006, and it was designed to understand activity in the sun from the surface layer, so the surface that we see if we look in visible light out into the hot atmosphere, and to understand dynamically what's happening. So we have spectrometers that can measure the flows, what comes towards us, the density of that, what it's made of. And we do that. We do campaigns where we're trying to understand what causes a solar flare. So looking at these really energetic explosions, most energetic things in the solar system that happen, but what actually triggers them. We are still at a stage where we we can't say tomorrow there will be a solar flare at this point in the sun and it's going to be geo-effective and it will hit us. So we are not at that stage yet. So looking at that early stage of the trigger is something that's been done a lot. Also looking at possible sources of the solar wind, because we can measure the flow, so we can measure what's coming towards us from the sun spectroscopically. So those kind of things are what we can do with that mission. And Hinode has been observing with opportunities from Parker Solar Probe during its different encounters. And we've been practicing and doing some observing just in this past couple of weeks with Hinode and Solar Orbiter. And that will also help with the calibration of the instruments that we spoke a bit about earlier, to make sure that the instruments haven't changed during orbit. Of course, you calibrate them on the ground, but something can change during the launch, or it can change due to the temperature environment or whatever. So those kind of things, all those missions working together. It sounds like there are a lot of missions, but they are all doing quite different things in a way. And working together, having something going as close as Parker Solar Probe is also, it's showing us completely new view of what the solar wind is and how it behaves. And it's just, as it gets closer, we'll just get to see more and more unusual things about what the sun is doing.
So what's the total lifespan of Solar Orbiter? I mean, what's the mission length? How long can we expect to be getting these revelations back?
The mission is designed to last for 10 years. And there's a very good reason for that. Well, first, of course, we are interested to use it as long as we can. But second, we also have a good reason to needing it for that many years, because the Venus flybys will help us slowly increase the orbit of the satellite out of the ecliptic plane. So the ecliptic plane is where all the planets fly around the sun. But one of the main goals of the mission is also to see for the very first time the poles, the solar poles. And to do that, of course, you have to get out of this ecliptic plane. And so Solar Orbiter will be the first mission with telescopes on board that will actually be able to observe the solar poles. And we are really excited about that. But of course, to get there, you need time, because you need several of those Venus flybys before you can crank up the orbit. So these the last years of these 10 years are very important actually for this polar science. So from 2025, 2026 onwards, we will get better and better views on the poles.
So just for, if I can remember it correctly, when I arrived at ESA in 2009, that was pretty much the end of the Ulysses mission, which had been flying a joint ESA-NASA mission. And that actually did go over the poles of the sun, but of course not with cameras on board. But that was fascinating, wasn't it? Because the way that worked is it actually went out to Jupiter and then used the gravity of Jupiter to pick it up and loft it, if you like, over the top of the sun, and then be in orbit around the sun 90 degrees perpendicular to all of the planets. Remarkable, right? I want to study the sun, so let's go the other way completely.
Yeah, indeed, it's quite interesting to see what kind of maneuvers you have to do with these spacecraft before you get them where you want them.
But the one I wanted to pick you up on, though, is that you said that Solar Orbiter would be the first one with imaging cameras on board to see the poles. That's not quite true, because you worked on a mission, Proba 2, which has actually managed to do that. And that's slightly odd because it's located close to the Earth. How was Proba 2 able to get those images just slightly looking down on the poles of the sun? Not from above, but at a very glancing angle. People don't really quite understand how that's possible without lifting yourself up.
No, that actually has to do more with the tilt. We see with how the Earth axis is tilted with respect to the sun, and also the sun rotation axis is slightly tilted. So from Earth, you can indeed see around March and September, you have times where you can see up to 6 degrees out of these. If you look in solar coordinates, you would see 6 degrees above the equator. And so you get a glimpse of one of the poles. So in that sense, indeed, we have had some glimpses of the poles. Now, the problem is, of course, you have a lot of effects there just because of the line of sight. So you can't really see properly, for example, how the magnetic field is formed there, because you see it from the side and you get a lot of weird effects because it's getting close to the limb and you have limb shortening effects. So it's very difficult to interpret what you actually see and what you actually measure. So that's why it will be important for Solar Orbiter then to see it from a better viewing angle. And so we hope to understand much better the magnetic field at the poles, also the evolution there, because the poles, these are kind of the key areas on the sun to understand better the solar cycle, why exactly it's 11 years, and how actually the sun prepares for the next cycle to start. It's also, the poles are also important because they produce a different type of solar wind. So because of Ulysses, actually, we learned that the solar wind, you have kind of two types of solar wind. Well, there are many gray areas in between as well, but you have the fast solar wind that comes from those polar regions. And then you have the slow solar wind, which is coming more from the area closer to the equator where all the active regions are. And so these different types of winds not only have a different velocity, but also different composition and different structure. And so this is one of the main goals as well of Solar Orbiter, to link those, to measure the wind and look at the same time at the source region of the wind. And we want to do that both for slow and for fast solar wind.
So Louise, what's the weirdest thing we can suspect we might see at the poles? I mean, I'm just thinking of Jupiter and Saturn, which have remarkable features at their poles, hexagonal structures, lots of sort of cyclones within cyclones within cyclones. Is it feasible we might see something completely weird at the poles of the sun, or does the physics rule that out?
I don't think the physics rules that out, because we are in a position that we understand a lot about the sun, but as Anik said, understanding the solar cycle, the models do aim to try and make predictions, and they can make predictions to a certain extent, but because the boundary conditions are not there at the poles, you can't constrain things well, or as well as you could. So we think we have an idea from models and from that sort of sneak peek view that you can get from the tilt twice a year of what the poles might look like. But we have never had that view looking down. So I'm expecting to be surprised by what we see. And I mean, I can't guess what will be there, but we know that the poles are very dynamic. Because we can see from X-ray images and so on, there's lots of activity there. It isn't just a blank area. It is an area that is active. There is magnetic field there that's changing a lot. And the way that field changes is different from the North to the South Pole. It doesn't work in sync. So there is this lag between the North and the South. So why does that happen? I mean, there's a lot of things that we just don't know. So I can't wait to see that, as we get slow. And it's like this build up of anticipation, because 2025 we're at 8 degrees and then you slowly go up, and each year you'll get a little bit more. And so, yeah, it's a game of patience.
So let's talk a bit then about this whole business of the solar cycle, because one of the things, what is making it happen, but sort of stepping back from that, thinking instrumentally, you've talked about the in situ instruments which measure the particles and the fields coming past. We've talked about the remote sensing instruments in the sense of taking pictures of what's on the sun or around the sun. But what we haven't talked about, you can see inside the sun. We can actually get, by measuring what's going on the surface very carefully, and I'll let you talk us through how we do that, we can actually infer the interior structure of the sun, and that's where the solar cycle is taking place, the shifting of material and changing around on this period. So how can we see inside the sun when it's a great blazing ball of gas, we're shining there in the sky? How do we do that? So
we use we basically steal a technique from Earth seismology, right? So you're measuring waves inside the sun, and you're able to do that through spectroscopy. So that all inside the sun is moving, it's dynamic, it's boiling inside, and that movement is what you're measuring. So you're seeing how sound waves bounce around inside, and you're able to measure those. So helioseismology is something that is an aim of Solar Orbiter. It's one of the science goals, is to try and measure what's happening inside, to understand where that magnetic field is coming from. So it is a methodology that has been tried and tested in a number of missions, and the results are absolutely fascinating, with these different flows that you can see how things are being dragged in different directions on the sun, and how that cycle propagates. So using that seismology technique will be really, really interesting at the poles. So that is something that observing campaigns will be carried out for. It's a difficult thing to do, for sure.
Yeah. So Anik, I'm just sort of thinking about what people think about the sun. It's not a rigid body that just rotates. It's kind of a floppy ball of stuff, and stuff is moving differentially at different latitudes, but also internally stuff is moving up towards the poles and then flowing back down again. Talk us through the basic structure of the sun, because again, most people in the audience don't, they sort of think it's just a big ball of fusing gas. It isn't really. It's quite structured in different pieces.
Yeah, indeed. We have different layers that we call the interior of the sun. So actually the surface of the sun we typically call, that's the photosphere. And this is the layer where most of the visible light comes from. And that's kind of, I think, why we call it the surface, because you can't easily look inside that. But so indeed, in the very core of the star, there is where the nuclear fusion takes place. And so this is where actually most of where the hydrogen atoms will be fused together. And then we get energy out when helium atoms are being produced. And then this energy actually has to find its way out of the star. And the first layer, big layer, is a radiation zone, where actually it's really trying to escape by radiating, but colliding with many different particles. And it takes years and years before actually the light can escape from there. And then you have more the outer layer, which is the convection layer. So their energy is being transported in terms of movement, in terms of, it's more like a bubbling material there, a little bit like what you see when porridge is cooking. This is kind of what you see at the surface. So we get there these convection cells that we can see quite nicely, also from Earth with very big telescopes, and also from space, of course. And so there you see actually the hot material being pushed up, and then cooler material drains down again. And so there also, this material in the end, it's not gas, it's plasma. So it's gas that's being heated to so high temperatures that all the atoms are actually ionized. And so for that reason, you have an electrically conducting material. And if you add a magnetic field to that, actually the magnetic field will drag around all this plasma and will structure it. So an energetic plasma can't really escape from magnetic fields. And that's why we see these nice loop-like structures on the sun. So we can't measure easily the magnetic field structures themselves, but we can see them because the material is kind of caught up in these structures. So if you then add all that together, so you have the bubbling star, you have indeed, as you said, differential rotation. So it's not rotating as one solid body, but at the equator, it's rotating faster than at the poles. If you add it all together, then you get really a very complex structure of the magnetic field. It starts at minima. So at the beginning of the solar cycle, the magnetic field is relatively well, it's not just a dipole, it's more complex than a dipole, but okay, it resembles it a bit, but then it gets more and more complex. You get these active regions being formed, the sunspots, and so then you get a lot of activity. And the activity then also removes part of the tension out of that magnetic field, so that towards the end of the cycle again, it can relax a bit again into this dipole and the whole cycle starts again.
Yeah,
I
I've
hope
always.
I.
No, yeah, I mean, it just, I mean, I'm not a solar physicist at all, and it just boggles me. I mean, I've always loved the idea that, you know, it's just 1% of the volume of the sun that's actually involved in actually fusing hydrogen and helium. The rest of it's just a big thermal insulation blanket. It's kind of the most efficient thermos flask you could ever imagine. If you generate a bit of heat in the middle, it takes hundreds of thousand years before it ever cools down. So if we can ever build something like that, can keep your coffee warm for that long. Of course, it would have to be quite big, I suspect. But so, Alex, let me hand over to you. Maybe you've got some questions at this point.
So, indeed, and and I think one of the best ones is, I suppose, I mean, many eyes will be affixed on what's happening, just like the next few hours and days and so on. But how many people are actually on the mission itself? I mean, it's obviously more than just the people on the Zoom call. I mean, just like, how big is the team around Solar Orbiter? I mean, who's going to be watching perhaps the most intently and the most on the edge of their seat? Arguably, the least sleep. Go on.
That's actually a very good question, and I don't really know the number because there are so many. Because actually, if you look at the mission, it's really interesting how big a coordination effort it is, because you have all the instruments, for example, they have been built in institutes all over Europe. We also have an instrument being built in the US, and another sensor, part of another instrument. So you have all those institutes. Then you have the spacecraft itself that was built by Airbus UK, all under then supervision of the ESA site in the Netherlands. Then you have the people working in ESA site in Spain, where I work. So this is the Science Operations Center. And so we are actually coordinating kind of the planning of the science, and also making sure the data comes down and get into the archive. And so we do really a lot of the mission planning and then the downlink. And then, of course, you have the center in Darmstadt in Germany, where they are responsible of driving the spacecraft, of commanding the spacecraft, making sure everything stays safe, flight dynamics, who is making sure the orbit is as it should be. And so all those people together, and then I didn't even start mentioning all the scientists that, of course, want to use the data and are really eager and waiting for the science phase to happen. So I know for the launch, it was from Cape Canaveral, and we were very happy that actually in Cape Canaveral, you do have a chance to actually go and watch the launch. And there were at least 1,000 people, I think, from Europe flying over to see the launch. And these were really all people that were working on the mission or their family. And that was only a little part of it in the end. So it's really thousands of people who have some bit in this mission.
Yeah, I think that's, but perhaps you can pick up on that, Louise, because one of the things which is sometimes not quite appreciated is that ESA runs on a different model to NASA. So the way that, and it's, of course, nothing's completely true about this, but NASA effectively pays for everything on its missions. But in our missions, there's a combination of money between ESA, which pays effectively for the spacecraft and for the running of the mission, but the member states, our 22 countries which make up ESA, pay for the instruments in consortia, and they come together. So, as one of the PIs of one of the instruments, how do you go about doing that? When an opportunity comes up, how do you sort of start making phone calls and working out who's going to join in and who's going to raise the money? Because we don't give it to you in that sense. It's not quite the same model.
It is more complex in that way. So it is a coordination across different nations. And within the instrument I'm involved in, the countries involved are Belgium, UK, Switzerland, France, Germany.
You're going to forget one, aren't you?
I'm going to forget one, I know. But it's multiple countries, and they have different funding agencies, different ways the funding works, different timelines and different deadlines for proposals. So the coordination effort involved is quite significant to ensure that each country agrees that this is a priority, and that you coordinate to try and get the funding at the same time, so that you can put your different pieces of the instrument together at the same time. But I think the teams that work on these instruments certainly in this field, they have worked with each other and know each other very well. So I think we're used to dealing with, if issues come up, whether it's financial or technical or whatever, you're used to being able to deal with those or work together to solve it. So I think that the teams are very good at doing that, but it is definitely complex, because you can have a change of government somewhere which suddenly changes the funding that goes into science, or you can't predict what would happen in different countries.
Yeah. And of course, one of the things when we had a previous episode of Uplink with Daniel Muller and Miho Janvier, and this was last year. And one of the things that you've had to do as a team is do all of this during a pandemic. So you had the launch in February 2020, and that was it. I mean, I don't know, has the science team actually ever managed to meet en masse since then? Has there been an event? No. Because normally several times a year, the science teams would come together, in person, meet and exchange information and experience. And so how have you managed that? I mean, obviously you've done it this way as we're doing Uplink, but is that, from your previous experiences, both of you on other missions, has that changed things for the worse, maybe even for the better in some ways? I don't know. What's your experience been? Anik first, you're on the operations side, because that's kind of the leading edge. Every day you have to make things go ahead.
Yeah, the funny thing was we installed an old operations room in ESAC, and we never used it up to now. So that was the first funny thing. No, so indeed, it was quite a challenge because, as you say, after launch, there were a few weeks and then everybody was just at home. And normally this commissioning phase, so these early operations is very difficult. It's very complex, and you need people close together to really react quickly to things that are happening on board. Then the months later, SOC, so our Science Operations Center, had to take over, and we have to coordinate in the end 10 instruments, and everything is new for everybody. So you have to coordinate the sending of the commanding, then the constraint checking, all the modeling. And so normally, indeed, we come together several times a year in a working group to discuss all this. And now it all had to be done through telecoms. So the good thing was that we all knew each other quite well already. We had several years collaborating on this already, and that helps a lot, because then you know better how to communicate and you understand each other better. We were also lucky that the planning tool we designed was anyway designed to be able to work with many people together and many teams together, because even if we would be in a meeting, we knew many instrument teams have to kind of work on the plan at the same time in parallel. So this tool actually also allowed us to do exactly the same, but then from home. Of course, it's all much more difficult to coordinate it. So instead of a 2-day meeting, we now had, for example, a series of 4 or 5 telecoms before we could sort it out. So I'm definitely looking forward to go to some of the normal meetings again. But it's also true that in the meantime, we have proven that it can work. And I'm sure we will not do as many meetings as we did before. So we can now, I think we will go to some kind of hybrid state of meetings for the more complex planning, and maybe for the simpler periods in the mission, we will probably use the same approach as we did during COVID times. Which is.
And for you, Louise, from the scientific perspective, once you have data, and you have been getting data from the cruise phase, of course, many scientific collaborations operate through all sorts of tools like Slack and email and so on anyway. But there are times when you really need to get together in a room and just sort of chuck stuff at a blackboard or a whiteboard. So how have you adapted in that regard?
I think that is what the ad hoc conversations where you would come up with new ideas is missing a little bit. I mean, I think the operations team and the way that's worked has just been amazing. The fact that everything is more or less worked during the pandemic. I mean, it just has been incredible to see. And I think for these big teams, if something is thrown at you, which is a challenge, often you see that people can work together to solve it. So, I mean, we had something different with Hinode during that awful earthquake in Japan, where they were obviously badly affected. And during that, the push from the team in Japan was, we have to keep running the spacecraft. So we'll change the way we do it so that we could do that. And yes, there was effort put in, but these problems, I mean, we couldn't have predicted a pandemic, right?
Well, we probably could have done, actually, but not exactly when.
Not exactly.
A bit like the sun, the activity is going to happen, but when?
Yeah.
Exactly.
We didn't expect it so close after launch.
Yeah.
But I think, one of the things that you do miss is when you have these big events and you're not in the same room as people. So the opening of the doors and seeing the first image, it was, you're sitting on your own, sort of seeing it for the first time, and you want to share it with people. So that sort of thing is missing, and it's obviously more challenging for students who coming in who don't know people, early career people. It's more challenging for them for sure when they don't know people.
Yeah, I can't think of anything sadder than the whole of the EUI team sitting around with their sad glass of champagne saying, "Yay!"
Yeah, when all this is over, we will have to have a whole year of celebrating, because we couldn't celebrate any of those milestones.
Exactly. So before I hand back to Alex, just, because we've kind of transitioned in that sense, the science phase, when does it kick off? I understand, we say it's after the flyby, but I understand, and I'm not giving too much away. I don't think there's still work to be done on the spacecraft to get it ready for for this full science phase. So when do we expect the data start arriving? And the other critical question, I think, for you, Anik, is, we're used in some of our science missions, solar missions like SOHO and SEO, the images just come down and are in the archives immediately. That's probably not true with solar orbiting, because it's a different kind of observatory. So when will the science phase really kick in, and when will people be able to see the data and the images coming out?
Yes, that's indeed quite different on this mission. So first, because of the orbit, so at times we are close to Earth, and then it's very easy to get the data down. At other times, the spacecraft is at the far side of the sun, 2 AU away from Earth. So then, of course, you get hardly any data, and the only thing you get is kind of making sure the safety is fine. So you get some housekeeping, and you get a mini piece of science data just to see, okay, are the instruments still working as expected? So during such an orbit, also we have the in situ instruments, the sensors that will sense throughout the whole orbit. Now, the remote sensing instruments, these powerful telescopes, if we would let them run at high speed through the whole orbit, we can never, ever get this data down. For that, there are too many constraints on the mission. So that's why from the beginning, from the design, has been chosen to choose windows of opportunity where the most interesting science opportunities happen. So these are typically close to the sun, so at perihelion, and also the periods where you have very nice configurations, or where we can see the poles later in the mission. And so there are typically 3 windows of about 10 days in each orbit, so each 6 months, where the remote sensing observations will be concentrated in. And normally that was kind of it. And then they would have to switch off for the rest of the orbit. Now, the good news is that in cruise, we found out that actually the network of the antennas was more powerful than we had expected. So the data downlink was a bit better. Also, we tried out some tests with running a low telemetry synoptic campaign, so kind of regular science data, but at lower cadence and maybe a bit less quality, but still good enough to really look through the orbit and see what's happening. So this is what's going to start now starting in December, January. We will have much more regular remote sensing instrument observations, but still the real most of the observations will be concentrated around this perihelion, and that will be in March. So that's why even if nominal mission phase starts now, the actual high science, the first high science periods will be around March next year. And then we will get some of that data down in the weeks after. But then it's also a time when the spacecraft is moving further and further from Earth. So the data that's taken towards the end, even from perihelion and further, will take a while to come down. For some images or data, it will be a few weeks. For others, it may be months. So we have a storage on board where we can store all those data until the satellite is coming closer to Earth again. So this is very different in Solar Orbiter than in SDO or SOHO, for example.
Yeah. So as you say, you know, we because the distance to the Earth changes, we go from being a mission with high-speed broadband to a dial-up modem at some point, right, where the data rate just drops colossally, you know, way down.
Yeah, it's really, it's like sometimes we only get, well, in the worst periods, we get less than 1 gigabyte per day down. And there are also times where there's even a blackout because the satellite is really moving at the far side of the sun in eclipse, so to say.
Yeah, yeah.
How much sleep are you both going to get over the next few days?
Yeah, well, I'm getting a bit nervous, especially with this extra satellite and the extra debris cost. But okay, I must say in the last day or so, we got really good news from the predictions that hopefully everything will go fine. But yeah, it's a bit nerve-wracking.
I think all those things, any significant event like this is a bit scary because so much has been invested in this mission over 2 decades that you really don't want it to be hurt in any way.
Yeah, in a way it'll make because there are, as you both said, there are more Venus gravity assist maneuvers to come, quite a few of them, in order to lift the spacecraft out of the ecliptic and change its orbit furthermore. So they'll all seem really easy in retrospect after this one, right? How many have we done already? We've done 2, I think. Is that right? 2 Venus gravity assists.
Yes. Yeah. And there are another 5 or 6 to come after the Earth GAN.
Yeah. Remarkable. I mean, and I think, you know, I think we've seen lots of flybys in lots of missions. I mean, Rosetta famously, but Bepi Colombo has been doing a whole series as well. I mean, the remarkable skill of being able to sort of direct the spacecraft to the accuracy needed both in speed and in location. Of course, we're not flying it on the joystick. I mean, sometimes people get the idea it's will I fly? It's all kind of calm and collected and worked out in advance. But this one, again, as we said, is weird because of all the junk. And that, you know, those well, as they used to say for the Hubble Space Telescope, and it's kind of semi-legendary, that lots of impacts on Hubble are thought to be due to the servicing missions and frozen urine that's been dumped overboard from the shuttle. So there's all sorts of stuff in space. We really don't want to talk about what might
don't want to go.
Oh, so that's one of the reasons we keep the doors closed.
We don't want any pee on your camera, Louise.
Yeah.
No, that would be disappointing, wouldn't it?
Yeah, if you think about these sensitive filters and especially with UV instruments, this is a very big point. I mean, everything has to be extremely clean. That was one of the challenges as well while building the spacecraft, to make sure that the environment was always very, very clean.
And the filters are so delicate. I mean, you can't say if you sneeze on it, it would disintegrate. The filters, so there's such a delicate thing. So, yeah,
amazing.
Well,
I mean, just to pick up on that, of course, the spacecraft is not only clean in terms of not stuff on it, but it's very magnetically clean as a spacecraft as well, because we've got these big magnetometer booms which are up here. And if you've got anything really magnetic on the spacecraft, it just screws them up completely, right? So that was a huge part of the campaign, I think, making sure that Solar Orbiter was as magnetically clean as possible.
Yes, that has been one of the bigger challenges, because in the end, it's very nice that we have a lot of complementary instruments on board, and the whole mission actually is driven by this idea of we look at something and then we measure the effect of it later. But it also means you combine very different types of instruments that have very different requirements. So indeed, the telescopes have a lot of mechanisms and complicated stuff also, because they have to measure and observe very close to the sun, but also very far from the sun. So the thermal environment is very different, the resolution is different, everything is different. So they have to recalibrate, they have to tune again, they have to focus again. So they have a lot of mechanisms on board. And then on the other hand, you have the sensors who just do not want any noise at all. So they do not want changing power. They don't want any of those disturbances. So those two living together has been a challenge, both in building the spacecraft and now also in operating it. But we are finding our way.
Indeed. Well, all that and the added dimension of frozen space Pete, I think adding a dimension of drama that I'm sure I speak for everybody watching tonight was unexpected, but equally tantalizing. Well, and on behalf of everyone watching tonight, I have to say, Louise and Anik, what an absolute pleasure it's been to have you here. We'll be thinking not just about Stellar Orbiter over the next few days, but also about you and the remarkable team as well behind it all as it completes this incredible maneuver. Now, before you go, Mark might have warned you, or possibly not, that there's a ritual that we have on here, and it's not just crossing fingers. It's another finger thing going on here. Mark, shall we?
I never warn anybody, because if I did, it would be too silly. So we have this hand signal. This is space. This is the Vulcan salute for space. Live long and prosper. And then, of course, rocks. Space rocks. So there you go. So it's good for social media. What can we say? Thank you very much.
Indeed.
It's been a great pleasure, and look forward to seeing. So, of course, it's early in the morning. Anybody in Europe probably, well, sensibly will be asleep if you're not part of the Solar Orbiter team. It's 4:30 in the morning, if I understand, GMT, so 5:30 for European observers. But you'll be keeping us updated on everything going well. I'm sure we'll hear great news early in the morning. We're not expecting any images back from this, if I understand. We didn't get anything back from the Venus flyby. Bepi Colombo has been able to use its webcams on board, but we won't see any pictures from this flyby, I think. But Solo High, maybe.
Solo High, yes. Solo High probably will have something. Also for Venus, they had some observations. They had actually.
Oh, that's true. Yeah, Venus did pass through the field of view. That's right. Yeah,
Indeed.
yeah. But do you know if? I mean, Earth should be in the field of view, because the field of view is effectively, well, it's pointing towards the sun, but as the spacecraft moves around the Earth, Solo High, at some point the Earth will be in the field of view. So maybe we can see all that light pollution from the ground or something like that on the night side of the Earth. Great stuff. Anyway, so we look forward to that. Good luck to everybody on the teams, and we'd love to have you back at some point to talk about the science results when we've got more of those in the years to come. And let's see what we see at the poles. I think that really is one of the most exciting things, right? I mean, just wouldn't it be amazing if there's a hexagon or something up there like there is on Saturn? What amazing. Anyway, that's great stuff for this evening. So thank you very much both, and we'll see you soon.
Thank you. Take care.
All right. Bye-bye now.
Bye-bye.
Well then, Mark, as ever, pretty much everybody that I meet in the world of space exploration, I kind of want to take to Vegas, because everybody's just such a cool operator. You know, it's just like, think about what's going on, and it's just it's a lot to think about. Don't know if I'd be able to handle it, really.
It's one of those things I've been asked a lot, you know, are you nervous when the launch is taking place? And you sort of think, well, yes, but it's what comes next, and it's this bit and it's that bit. And at some point, I think you just learn to you have to accommodate it. I mean, it can be risky. It's a high stakes game. You know the technology is always at the bleeding edge. You've tested it to the nth degree, and you hope and you think it's going to work, but sometimes things jump up at you. And what's amazing about the teams that work on these missions is even when there are problems, they find ways of dealing with it. And we talked to Richard Southworth and Eric Kulkers recently on the Integral mission, and how they solved very rapidly this tumbling issue, which threatened the mission. And we've seen problems on other of our missions. And it comes back, I think, a little bit to that thing that Anik said, is the teams get to know each other over years. And they're trained together, they've worked together, and that human connection, technology allowing, I mean, of course, sometimes things happen which you can't do anything about, but that ability to work together as a team across Europe and across the world and solve problems is, you know, it underpins the missions, but it underpins what we're trying to achieve with the science as well. Taking on challenging questions, you know, how do we solve climate change? Well, we're not going to solve it by either ignoring it or wishing it away. We solve it like this. We build groups of people with expertise, complementary expertise, and we bring them together, and we we figure out. Then we have to get everybody else to come along with that, which of course is a whole nother socio-dynamic issue. But
indeed. Well, remarkable machines and remarkable people behind them as well. We'll be thinking about Anik and Louise as this all takes place. And Anik did mention, fingers crossed, eh? Let's just see what happens.
Yeah,
Very
absolutely. Good. Yeah, I'm sure it'll be okay, but it comes with that frisson, which keeps everything fresh.
Indeed.
Yeah.
Indeed. Mark, as ever, a pleasure to see you, and we'll catch you next time.
Yeah. Thanks, everybody. Good night.
Thank you.